The carburetor supplies the engine with the correct mixture to suit all operating conditions, from idling to high speed. To do this, it has a number of systems. With the engine stopped, the throttle valve is closed, but fuel is still held in the bowl. With the engine running, fuel is held at a set level by the float and a needle valve. Fuel supplied to the engine when it is running is replaced by fuel from the tank. A passage from the air horn to the float bowl balances air pressure between the air cleaner and the float bowl. The idle air passage and the main discharge nozzle are above the level of the fuel. The first stage of the idle system uses the idle and low speed circuit, plus an idle adjustment screw. The throttle valve is almost closed, so airflow through the carburetor is very small. The action of the piston creates a low pressure area below the throttle, and this is concentrated at the edge of the throttle valve as the air passes the idle port. Fuel flows from the float bowl through the idle passages and into the carburetor below the throttle valve at the idle port. The air bleed lets air enter the fuel on its way from the float bowl. This helps aerate the fuel before it reaches the idle port. Engine idle speed is set by two different adjustments. The amount of fuel is adjusted by the mixture adjustment screw at the idle port. The amount of air is adjusted by changing the throttle stop screw. Second stage idling starts as the throttle valve opens. This is similar to idle, but with the low speed port uncovered. Both ports discharge fuel to mix with incoming air. Low speed ports help the transition from idling to low speed to high speed. Without them, the engine tends to hesitate until the main system comes fully into action.
The carburetor supplies the engine with the correct air-fuel mixture for all conditions of operation. It atomizes the fuel and mixes it with air. It controls the delivery of this correct mixture to the engine. Carburetors come in different designs. This is a basic downdraft carburetor with a fixed-size venturi. Fuel is pumped to the float bowl, where a float and a needle valve control its level. The float bowl is open to the atmosphere. The barrel of the carburetor has an air horn and a venturi. A throttle valve below the venturi is linked to the accelerator pedal. Its action allows airflow into the carburetor barrel. The shape of the venturi constricts airflow and lowers pressure there. The pressure difference between the bowl and the venturi causes fuel to spray out of the fuel discharge nozzle. It mixes with the air, and the mixture passes the throttle valve and enters the intake manifold and the engine. Depressing the accelerator increases airspeed through the carburetor. This lowers air pressure at the nozzle. Atmospheric pressure on fuel in the float bowl stays constant, so more fuel is forced into the venturi to mix with the increased air. This keeps the air-fuel ratio roughly constant for a range of throttle openings. The throttle valve also controls flow of mixture into the engine. Opening it lets more mixture be delivered, which increases engine power and speed. Closing it has the opposite effect. The main or high-speed system comes into action above fast idle, as airflow through the venturi increases. A main metering jet in the fuel in the bowl meters fuel passing into the discharge nozzle. How much fuel leaves the nozzle depends on the pressure difference created by the airflow through the venturi. As the throttle opens and airflow increases and speeds up, more and more fuel is drawn from the discharge nozzle. However, the mass of air doesn't increase in proportion with the speed, and as a result high speeds can produce a mixture that is too rich. To correct this, more air can be added. This is called compensation by air correction. As the throttle opens and engine speed increases, the level in the jet well falls, exposing air bleed holes in the discharge tube. Air can now mix with the fuel and stop the mixture becoming too rich. As the throttle opens further, the fuel level falls too, exposing more air holes. More air bleeds in to maintain the correct mixture. The size of the main jet is selected to provide the best mixture for economy under cruising conditions. When the throttle is open wide for maximum power, a richer mixture is required. The extra fuel is provided by a power jet with a vacuum piston and rod opening it as it is needed. At low speeds, intake manifold vacuum is transferred through a passage to the vacuum piston. This holds the piston up and keeps the power valve closed. With the throttle valve fully open for full engine power, the vacuum in the intake manifold falls. A spring pushes down the vacuum piston and rod to open the power valve. Fuel flows through a bypass jet to enter the fuel well and add to the fuel from the main jet. This provides the extra fuel needed to enrich the mixture for full power.
Extra fuel is also needed for accelerating. Suddenly opening the throttle increases the airflow, but fuel cannot flow from the discharge nozzle quickly enough to match it. An extra jet of fuel is needed. Depressing the pedal compresses a duration spring that exerts a force on the plunger of a small plunger pump. This pressurizes fuel below the plunger and closes off the inlet valve. Fuel flows through a bypass jet and enters the airstream from a discharge nozzle above the venturi. The duration spring extends the time for delivering the fuel. Releasing the pedal lets the linkage move the plunger upwards. The bypass jet closes and the inlet valve opens to let fuel refill the pump chamber from the float bowl. When a cold engine is being started, little air flows through the venturi, and there is no heat to assist in vaporizing any fuel that is delivered. This makes the effective mixture of fuel and air too weak to be readily ignited by the spark plug. An excess of fuel must be supplied temporarily to ensure that the proportion of fuel that does vaporize will form an ignitable mixture. A choke valve is fitted to help. Closing the choke valve closes the carburetor intake. The pumping action of the pistons creates a low pressure area below the valve even without venturi action. This low pressure causes fuel to flow from the discharge nozzle and from the idle and low speed ports, and provides the rich mixture needed to start the cold engine. The choke can be controlled manually by a cable that operates the valve. Most are controlled automatically, so that the valve is closed when the engine is cold and opens progressively as the engine warms up. When the engine is warm, the fuel drawn into the manifold during starting vaporizes readily, and the engine can be started without the aid of a choke. The choke should operate as briefly as possible. Overusing it produces rich mixtures that cause exhaust pollution and increase fuel consumption. Flooding a carburetor also produces rich mixtures. This can be caused by wear or by dirt trapped in the needle and seat that causes the level in the float bowl to rise and fuel to discharge from the nozzle, with little or no venturi action.
Carburetors can have a single barrel or 2 or 4 barrels. Extra barrels improve performance, particularly at high speeds, letting more air enter the cylinders than with a single barrel. 2-barrel carburetors have 2 outlets to the inlet manifold and have 2 basic designs. One has a common float chamber, but each barrel has a complete set of all other circuits, and the throttles can open simultaneously. The float chamber may be straddled by 2 connected floats that almost surround the air passage. This leaves it unaffected by cornering, climbing, accelerating or braking. The other basic design has throttles that open in 2 stages. It combines the 2 barrels to act as a single carburetor. The 2 stages combine good low-speed operation of a single barrel design with the extra airflow of 2 barrels. One half of the carburetor has all the circuits needed to supply mixtures for the whole range of operation. This is called the primary side. The other barrel, the secondary side, supplies extra mixture, but only at high speed or full throttle. It normally has a main metering system and a non-adjustable idling system. The primary side has a choke for cold starting. When the engine is being started, the throttle on the secondary side is already closed, so a choke isn't needed. From idle to medium speeds, only the primary throttle is open. When engine speed rises to where additional breathing capacity is needed, the secondary throttle opens to admit more air-fuel mixture. By the time the primary throttle is wide open, so is the secondary throttle. This can be controlled mechanically or by a vacuum unit connected by pull rod to a lever on the secondary shaft. When air flows past ports in the Venturis, it produces low pressure areas. A hose transmits this low pressure to a diaphragm chamber. This low pressure acts on the diaphragm and opens the secondary throttle. Large capacity V8 engines may use a 4-barrel carburetor of two-stage design, effectively two-stage carburetors combined, with each side supplying 4 of the 8 cylinders. A central moulded plastic fuel ball and suspended metering system can be incorporated into the design. This gives lower fuel temperatures with more precise fuel metering and closer control over air-fuel ratios.
Fuel pumps on carbureted systems can be electrical or mechanical. The mechanical fuel pump for the carburetor system is usually mounted on the cylinder head or the engine block. It has a flexible diaphragm. That's a flexible piece of neoprene rubber separating two chambers. This diaphragm is operated by an eccentric on the camshaft. It rotates, making the rocker arm move. This movement is transferred to the diaphragm, pulling it down. That draws fuel into the pumping chamber above the diaphragm. The diaphragm spring moves the diaphragm up, and this forces fuel from the pumping chamber out of the pump and into the carburetor. When the engine needs more fuel, the diaphragm moves through a long stroke to pump a lot of fuel. When less fuel is needed, pressure builds up in the fuel line to the carburetor and in the pumping chamber above the diaphragm. The diaphragm spring can't push the diaphragm up so far, and the pumping stroke is reduced. Some pumps also have a return line to send excess fuel back to the tank. As the fuel circulates, it cools the fuel pump and lines and reduces the chance of vapor locks. Carburetor systems can also use electric fuel pumps. Most of these pumps are located outside the tank, though some are inside the tank. One widely used pump is the diaphragm type. It has an electrical section and a mechanical section. When the ignition is switched on, current magnetizes the solenoid. The magnetic field energizes the armature, which pulls down the diaphragm. This creates an area of low pressure that draws fuel into the pump. Pulling down the diaphragm breaks the circuit and stops the current. The solenoid is no longer an electromagnet. The armature is released and the diaphragm spring forces the diaphragm up, which forces fuel out of the pump and on its way to the carburetor. This action continues, delivering fuel each time. When the engine needs less fuel, pressure builds up in the fuel lines to the carburetor and reduces how much fuel is delivered. Some carburetor-equipped vehicles with electric pumps have a safety switch that prevents the pump continuing to run if the engine stops.
A tachometer is used to indicate engine RPM. It's normally connected to the negative terminal of the ignition coil. The pulses from the ignition primary circuit are then used as an input to operate the tachometer. At idle speed, the frequency of the pulse is steady. As the engine speed rises, the frequency of the pulse increases, as the tachometer indicates. A tachometric relay uses the same input from the negative side of the ignition coil to ensure the relay operates only when engine speed is above a specified minimum, say 350 rpm. In this case, it operates as a safety device, ensuring the fuel pump operates only when the engine speed exceeds this figure.
Where the tank is mounted depends on where the engine is and on space and styling. Safety demands that it is positioned well away from heated components and outside the passenger compartment. Most tanks are made of tinned sheet steel that has been pressed into shape. Some passenger car tanks are made of non-metallic materials. Aluminum or steel is used on commercial vehicles. The tank is usually in two parts, joined by a continuous weld around the flanges where the parts fit together. Baffles make the tank more rigid. They also stop surging of fuel and ensure fuel is available at the pickup tube. Fuel expands and contracts as temperature rises and falls, so fuel tanks are vented to let them breathe. Modern emission controls prevent tanks being vented directly to the atmosphere. They must use evaporative control systems. Vapor from the fuel tank is trapped in a charcoal canister and stored there until it is burned in the engine. A vapor or vent line with a check valve connects the space above the liquid fuel with the canister. This valve opens when pressure starts to rise and lets vapor through but not liquid. Liquid fuel closes the check valve and blocks the line, stopping liquid fuel reaching the charcoal. Some systems have a small container, called a liquid vapor separator, above the fuel tank. It also prevents liquid fuel reaching the charcoal. This fuel tank has a small separator tank and a number of vents. They're from different parts of the tank, so that for as many vehicle positions as possible, at least one is always above the level of fuel in the tank. Fuel lines are usually made of metal tubing or synthetic materials. A fuel supply line carries fuel from the tank to the engine. A return line may also be provided to allow excess fuel to return to the tank. This helps prevent the formation of vapor that can occur in the fuel supply during hot conditions. The fuel filler is where fuel enters the system. The filler neck is a pipe that extends above the fuel tank. On unleaded gasoline vehicles with catalytic converters, the filler neck is designed to prevent leaded fuel being added. Its diameter is smaller than those on leaded vehicles, and a trapdoor inside the filler can only be opened by the nozzle of the unleaded fuel spout. The filler cap seals the filler neck to keep out water and foreign objects. Water can corrode internal passages of fuel pumps and carburetors. The cap on the fuel tank also stops fuel vapor escaping and polluting the atmosphere. This is important for gasoline, which is very volatile and vaporizes easily, especially in warmer climates. Some fuel caps have a low-pressure valve built in. It keeps a balance between the pressure in the tank and the outside atmospheric pressure. As fuel in the tank is used, the airspace above the fuel increases. This causes a fall in pressure compared to outside atmospheric pressure. The valve then opens and lets more air into the tank. A fall in temperature can cause a fall in the pressure in the tank. The valve opens to admit more air till inside and outside pressures equalize again. The fuel gauge shows how much fuel is still in the tank. It has a gauge unit on the dash and a sender unit in the tank. This unit indicates the level of fuel in the tank and transmits this information to the gauge in the dash panel.
The charcoal canister is a canister of activated charcoal, and it's a temporary storage device for vapor from the tank. When the engine is stopped, vapour from the tank passes through the vent pipe to the canister and is absorbed into the charcoal. When the engine is running, the lower pressure in the inlet manifold draws in the petrol vapour from the charcoal into the manifold. The process is controlled so it doesn't upset the air-fuel mixture.
Fuel must be kept clean, or the jets in the carburetor could be blocked, or corrosion can occur. So fuel systems always contain filters. In this carbureted system, a fine filter of nylon or gauze is fitted to the pickup pipe in the gas tank. A large surface area is provided to allow adequate flow rate and better filtering. An inline filter, usually made of clear plastic, is either between the tank and the pump or between the pump and carburetor. This filter traps dirt and water. The amount of water can usually be seen through the plastic.